In the next examples, we'll look at the idea of someone in a lift and think about the forces acting on them. So here's our someone. Remember, we don't want to particularly make it look lifelike. You're standing in a lift. The earth is trying to pull you down. Your weight is still acting on you. You don't fall because the floor is pushing you up. We can call that a reaction force, right? But I like to use R because if you're standing on a set of scales, it's that force that the scales are going to measure. Now, as we'll see in a second, when the lift's stationary, if you're standing just in a normal floor, then R will equal W, and that's how scales read your weight. Right, but that's a special case, they don't always read your weight, as we see in a wee second. So as usual, the same method applies. Fun is R minus W. So we draw a diagram, we get an expression for fun in that particular case. Then using Newton's second law, we can say MA equals R minus W. And what this does is enables us to link the acceleration of the lift to the value of R. M is fixed, and because of that, W is fixed. It's just mg, remember. And basically what we can do is look at common situations then. If you're at rest, then A is equal to 0. So if we look at that formula there, if A is equal to 0, then MA is 0, i.e. R minus W equals 0. Or rearranging that, we get R equals W. But that's also true for constant velocity. By definition, acceleration is equal to 0. So R minus W equals 0 as R is equal to W. So when we were in the lift, we had that initial acceleration of the lift when it started moving, but then once it settled to a constant speed in between the floors, your weight reading went back to, this reading in the scales went back to being your weight. So they're grouped together. We can also group together some other motions. Right? When you first get in a lift, we'll make it a wee bit easier this time and start at bottom floor. If you accelerate upwards, then A is positive. Now the other motion that can give you a positive acceleration is decelerate down. So both of them give you A is positive. That means R minus W is positive, and that can only be the case then if R is greater than W. So when the lift is accelerating up, right, so if you get in a bottom floor and press the button to start going up, then the reading in the scales will be greater than your weight. And that's what your body senses. You feel heavier at that point. When you're going down, so when you're already moving and you start to slow down as you approach a bottom floor, then once again you feel heavier. The reading in the scales is greater than the weight. Basically, in both of those cases, the floor's got to push you up more than your weight in order to produce the change that's needed. Right? Either to speed you up if you're going up the way, or to slow you down if you're coming down the way. And the last types of motion we can group together. If you decelerate up, okay, so if you're in your lift and you're approaching a top floor, as you start to slow down, then A is negative. But accelerating down has the exact same effect. So when you're in a top floor and start moving down. In both of those cases, A is negative, so R minus W must be negative, i.e. R must be less than W. And at that point, the reading in the scales and how you feel is lighter than your normal weight.